In this video, we will continue investigating the concepts of absolutely convergent and conditionally convergent. So as a reminder, given a series, we can now break it up into three classifications. So originally it was just this classification of divergence versus convergence. Now what we're going to do is take the convergence category and break it down into two possibilities. There's the possibility of absolute convergence, which means that the sum of the absolute values of the A sub n converges. Then there is the possibility of conditional convergence, which implies that the series itself converges, so it's a type of convergence, but the series is not absolutely convergent. And for the example that we saw in the previous video, we used our previous test, in that case it was an alternating series test, to see that the series converges, and then we just checked that it was not absolutely convergent. But there is another test we can use that actually allows us to make that classification of absolute convergence. So we've previously encountered the ratio test, and it was a version of the ratio test which was specifically for series with all positive terms. So this is also called the ratio test. The book will typically include the extra word in here, the absolute ratio test. And the absolute ratio test is meant for series with non-zero terms. But similarly, you calculate the limit as n goes to infinity, now the absolute value of an plus 1 over an. And if you get back some number rho which is less than 1, you get absolute convergence. Bigger than 1, divergence. Equals to 1, inclusive. And if it is inconclusive, there is absolutely no conclusion we can make. It might converge absolutely, it might converge conditionally, and it might diverge. All three are possibilities. And once again, the typical scenario when you would use the ratio test is when you have powers and or factorials present. So let's look at a few more examples. Based upon the form given here, that's determined if the series is conditionally convergent, absolutely convergent, or divergent. Based upon having a whole bunch of powers present, right? Minus 1 to the n to the fourth, 2 to the n, those are indications that we could use a ratio test. So our a sub n in this case is minus 1 to the n to the fourth over 2 to the n. So for that ratio test, we need to calculate the limit as n approaches infinity now of the absolute value of an plus 1 over an. So this will be the limit as n approaches infinity, absolute value, an plus 1. We look up at a sub n, and each of the three spots we see an n, we replace that with an n plus 1. So minus 1 to the n plus 1, n plus 1 to the fourth, 2 to the n plus 1. And once again, instead of dividing by a sub n, what we do is we multiply by its reciprocal. So we'll multiply by 2 to the n, divide it by minus 1 to the n to the fourth. And the first observation I want to make is because we have absolute values, the minus 1 to the n plus 1, the minus 1 to the n, simply go away. Furthermore, the 2 to the n on the top cancels off with n of the 2's on the bottom. So since the minus 1 to a powers are gone, we no longer need the absolute values. We have a 2 on the bottom which pulls out front as a 1/2. And then what remains is an n plus 1 to the fourth divided by an n to the fourth. And at this point we can simply write down the value of this limit. So you have the 1/2 hanging around out front. And if you imagined expanding out in the top, degree 4 over degree 4, leading coefficient 1, leading coefficient 1. So the value of that remaining limit is 1. Another way you can easily see that is you can think of taking this limit and plugging it in to that fourth power. So n plus 1 over n goes to 1, and 1 to the fourth is 1. So the value of the limit is 1/2. which is less than 1. So by the ratio test, so RT for ratio test, the series given here, the sum from n equals 1 to infinity, minus 1 to the n to the fourth over 2 to the n, is absolutely convergent. Once again, the reminder in terms of when the ratio test would be a good choice, typically it's when you have series that involves powers and or, so it could be both or one or the other, factorials. All right, one last example. Classify the given series, conditionally or absolutely convergent or divergent. So note we have an alternating series, and this doesn't look like something that would be applicable for the ratio test. So let's just see what the alternating series test tells us. So our b sub n in this case is square root n over 1 plus 2 square root n. And hopefully at this point you see exactly what's going to happen. So if we want to apply the alternating series test, we need to take the limit as n goes to infinity of our b sub n. And comparing the top and the bottom, you have the largest power of n in the top is 1/2, the largest power of n in the bottom is 1/2. So simply dividing the leading coefficients suggests that the value of this limit should be 1/2. Because it's not a rational function, that is, it's not a polynomial over a polynomial, you could do an extra step of work. That extra step of work would be to multiply by 1 over square root n, divide it by 1 over square root n. So in this case, you would have the limit as n goes to infinity of 1 over 1 divided by root n plus 2. The limit of a constant is that constant, and as n goes to infinity, that 1 over root n goes to 0. So when you take the limit of the b sub n, you end up with the number 1/2, which is not 0, so the alternating series test tells us nothing. But the conclusion that we can make, though, is that the given series diverges, and the reason it diverges is by the test for divergence.